Hello friends, welcome to today's lecture. So if you remember, we are solving this problem y of x equal to f of x plus lambda a to b k of x of t y of t dt, and here we have assumed that this kxt and fx are say L2 functions, and we try to find out the solution of this problem as y of x is equal to f of x plus lambda a to b gamma x of t lambda f of t d of t, where gamma x of t lambda is given as dx t lambda divided by d lambda, provided that d lambda is such that d lambda is not equal to 0. And we have seen that in previous lecture we have obtained the expression of d lambda, and in this lecture we try to find out the expression for a resolvent kernel given in this particular form. So we try to find out this expression for dxt lambda such that we can have the solution here. So please recall that the solution of this Fredholm integral equation can be written like this. So this portion we have already discussed for the case when kxt is given in terms of separable kernel, or we have already solved for say method of approximation. So here we have seen that the solution is given by this, and gamma xt lambda is given by the quotient here. So we have seen the d lambda. The only thing we want to see that is there any exist a resolvent kernel of this kind so that our solution can be written like this. So here if we remember, we have seen that this resolvent kernel satisfy the Fredholm integral equation. So it means that we want to find out a resolvent kernel gamma xt lambda such that it is given by this ratio of dxt lambda divided by d lambda and satisfy the following Fredholm integral equation. And if you remember, this we have already given in terms of say in the lecture when we discussed the method of successive approximation. There we also proved these two relation 27 and 28. Not proved, it is given in terms of this. So here this gamma xt lambda satisfy the Fredholm integral identities given as this: gamma xt lambda is equal to k of xt plus lambda a to b gamma xs lambda kst ds, and the other identities it is given as gamma xt lambda as k of xt plus lambda a to b kxs gamma xt lambda d of s. We are going to use this identity here. So here if I take this notation that gamma xt lambda is given by ratio of these two quantities, then you can write gamma xt lambda as dxt lambda divided by d lambda. So you can take d lambda the other side, and you can write this as dxt lambda as kxt d lambda plus lambda. Here also we have used a notation that gamma xt lambda as dst lambda divided by d lambda. So when you simplify, so this equation number 28 you can write it like this. So here when you write it this, then I can write here that your equation that gamma xt lambda satisfied is that gamma xt lambda is equal to k of xt plus lambda times a to b k of xs st gamma xs lambda d of s. Now here I am writing this as this. So here I can write d of x t lambda divided by d lambda equal to k of xt plus lambda times a to b. Here I am writing d xs lambda x s lambda divided by d lambda and k of st d of s. So d lambda you can multiply through all, and you can get that equation number 29 is valid. So here dxt lambda is written as kxt d lambda plus lambda times a to b dst lambda kxs d of s. So it means that if our solution which we want in this particular form yx equal to fx plus lambda a to b gamma xt lambda ft dt, where we want that this resolvent kernel can be written in this particular form. Why we are choosing this? Because we have already seen that in case of separable kernel your solution can be written like this. So here we want that in case when we have a general kernel, can we have the similar kind of solution, so that when we take kxt as a kernel which is separable, the same results are identical. The result obtained in separable case and result obtained here are identical, or we can say that we are generalizing the result which we obtained for separable kernel. So it means that to find out this, we try to find out dxt lambda, because d lambda which we have already obtained. So then we try to find out identifying the expression satisfied by dxt lambda, and we have seen that if gamma xt lambda which satisfy these Fredholm identities, then you can say that dxt lambda is something which satisfy this equation 29. So this is an integral equation satisfied by dxt lambda, and with the help of this equation number 29 we try to find out dxt lambda. So here we can say that if d lambda which we have obtained like this, then you can say that this is kind of a power series in terms of lambda. So this gives that if d lambda is a power series in terms of lambda, then dxt lambda which satisfy this equation number 29 will also be written in terms of power series in terms of lambda. And in a similar way, which we have already mentioned, that the convergence of d lambda can be discussed, in a similar way we can also discuss the convergence of dxt lambda. So let us assume first of all that the solution of equation number 29 can be written in terms of power series or in the parameter lambda. So looking at the expression given in terms of d lambda as a power series in terms of lambda, we assume that dxt lambda is also written in terms of power series in terms of lambda. So here we take the coefficient like this, c naught xt to cm xt m equal to 1 to infinity. We want to find out this cm xt coefficient cm xt such that dxt lambda satisfy the equation number 29. So here let us further simplify this notation. Let us write this d lambda as c naught plus m equal to 1 to infinity minus lambda to power m factorial m cm, where cm, if you look at what we have denoted here, cm is the coefficient of minus lambda to power m divided by factorial m, and it is given by this m fold integral of this quantity k x1 to xm and dx1 dx2 dxm. So here c naught is given by 1, which is obvious from this. So here we just writing d lambda in terms of this power series, and now with the value given as d lambda and the assumption that dxt lambda will be of this kind, we try to find out the relation which this cmxt satisfied, and hence we try to find out the expression this cmxt satisfied. So here to do this, what we try to do here, we write down the expression d lambda and dxt lambda in this equation number 29. So if you look at what we try to do, let me write it here. Just I am giving you a hint, you can do it on your own. So here I am writing d lambda as c naught plus summation minus lambda to power m factorial m and cm, small cm, and dxt lambda, it is c naught x of t plus summation minus lambda to power m factorial m. M is from 1 to infinity, here also m is equal to 1 to infinity, and this is capital cm x of t, and we want to find out cm xt because this cm c naught is 1 here, and cm is already obtained as this okay. So here your Cm is given by this m-fold integral. So here this is m-fold integral, integral, and k of x1 to say xm and x1 to xm. Notation we have already discussed. So with the values C naught Cm known to us, we try to find out dxt lambda. It means we need to find out C naught xt. Now we know that this dxt lambda satisfy this relation, this thing. So here dxt lambda is satisfying this relation. Dxt lambda is equal to kxt d lambda plus lambda times a to b t of s t lambda and k of x s d of s, or you can write it k of x dst lambda. So here let me write it here, C naught x of t plus summation m equal to 1 to infinity minus lambda to power m minus lambda to power m upon factorial m Cm x of t minus, I am just taking this kxt here, and you can write it here, no problem. This is what this I can write C naught plus summation m is from 1 to infinity minus lambda to power m, this is minus lambda factorial m Cm plus lambda times a to b, and here I am writing dxt lambda s, so you can write it kxs here, no problem, and then dst lambda in the same way. So it is C naught, I am writing st plus summation m is equal to 1 to infinity minus lambda to power m factorial m, and this is what Cm s of t, and this is integration with respect to Scm. So what we if you look at the constant term, C naught is simply 1, I can write it 1 here, and yeah, so here if you look at the constant term is what, so constant term on both the side is, here it is C naught x of t, and here rest are all containing lambda here, and here also so we have constant term given as k of xt. So k of xt as C naught xt. So if you compare the constant term on both the side, you can get C naught xt as k of xt. Now to find out Cm xt, so what is Cm xt? Cm xt I can consider as the coefficient of minus lambda to power m upon factorial m. So we need to find out the coefficient of minus lambda to power upon factorial m. So here, or you can say just find out the coefficient of minus lambda to power m. So it is what, factorial m, so this Cm xt into factorial m. So here I am just finding the coefficient of minus lambda to power m. So if you look at here, we have factorial m Cm xt now equal to kxt we have, and then here what we have as a coefficient of minus lambda to power m, that is Cm, small cm divided by factorial m. I think something wrong here, this is divided, this is not in multiplication, it is divided, factorial m, okay, plus now here since we have lambda here, so to find out the coefficient of minus lambda to power m, I need to find out only the coefficient of minus lambda to power m minus 1 times minus 1 minus. So here I can write this as minus, and what you will get integral a to b, you have k of xs and the coefficient of minus lambda to power m minus 1. So here that will be what, that will be your Cm minus 1 s of t d of s, is that okay? So and yeah, that is the thing. So this is the coefficient, this Cm minus 1 st is the coefficient of minus lambda to power m minus 1, is that okay? So yeah, then upon factorial m minus 1, there is a factorial m minus 1 here. So now multiply by factorial m here on throughout. So you can say that cmxt I am just multiplying by, so this factorial m you cancel out here because of divided by factorial m minus 1 we have this. So it means that your c naught xt is k of xt and cmxt is satisfying this integral equation given as this. So here we have this coefficients written is like this. So c naught xt is equal to k of xt and cmxt is given as cm kxt minus m kxs cm minus 1 st dfs. Now there is one more thing which you wanted to discuss as the relation between small cm and capital Cm minus 1. So here if you look at, we try to find out with the help of cmxt the last expression, that is small cm as given as integral of cm minus 1 x of s d of x. So here if you look at the expression here and try to find out c1 c2 and so on and see what it will be, right. Now claim is that this claim is that this cm x of t is given as, you can say that it is k of x t x1 to say xm, and here we have x1 to xm, and this is dx1 to dxm, and here we have m-fold integral. I hope because this is given here in terms of this thing, this is the dxt lambda, here is dx1 to dxm. So here we claim that your cmxt is given by this. So how we can show here that if you look at for m equal to 1, let us try to find out m equal to 1. So to find out c1 x of t is equal to k of xt and cm means c1. Now what is the value of c1 here? So if you look at what is the value of c1 here, c1 is we can obtain by c1 is the nothing but the coefficient of minus lambda to power minus lambda. So that you can say that c1 is nothing but integral of kxx. So c1 is integral of kxx d of x. Is that okay? Minus m a to b, and this is k of x of s. Now when m is equal to 1, then it is nothing but c naught s of t, and c naught s of t is nothing but k of s of t d of s. So for m equal to 1, you can say that c1 xt is given by this, and if you further simplify, you can further simplify as this. Since this is integration with respect to dx here, I can write this in terms of ds. So let us change the dummy variable here, let us write it in terms of s. So I can write this as integral k x of t. I can write this as k of ss d of s, and my m is 1 here basically, so m is simply 1, so I can remove this minus. So I am taking this minus sign out, so I can write it here. Yeah, so here I can write it a to b, and this is ds I am taking out. Here we have minus k of xs, k of s of t, this is whole as d of s, right. Now can we write it in a different version? So can I write it a to b, and here I am writing this as k of x okay. What we want is this notation. So this we want to claim. So we want to check whether it is this or not. So if you look at this expression is what? This expression a to b, and this is k of x of t and k of x of s and determinant of this, and here we have k of st and k of ss. So we want to check whether this is written or this not. So if you look at this is what? Kxt kss. So kxt kss minus k of xs into ks of t. So I hope that that this I can write it a to b k of x s t s d of s, right. So this is for m equal to 1, and we want to show that the similar expression is valid for a general m, right. So for that what we try to do here, we try to verify that if cmxt is given by this, then it will satisfy this equation, recurrence relation given by this. So for that this is a quite detailed one, for so I am not doing it, but I can say that what you try to do here, if you write down this is what? This is m integral, and this I can write this as m determinant of m here. So you can write it k of x t, k of x x1 and so on, k of x xm, and here we have k of x1 t and so on. So if you express, if you expand this around the first column, you do x1 to dxm, and if you expand this with respect to first column and simplify, you can say that this is given by this. Again I am not discussing the proof, but if you want to have the proof, it is given by W. V. Lowitt. So there you can find out the proof of this W. V. Lowitt, and the title of the book is Linear Integral Equation. So we can simply say that for m equal to 1, the C1xt is satisfying this relation, and for general m you can show that the expression given here is satisfying this, and for detailed proof of this you can refer this book W. V. Lowitt. Title of the book is Linear Integral Equation. So in this book not only you can find out the expression for cmxt, but also you can say that the convergence of dxt lambda is also discussed, as we have seen that the convergence of d lambda is discussed. So right now since it is involving, I am not writing the proof, but I am assuming that your cmxt is given by this and c0 xt is given by this, and cmxt can be obtained by this. In fact we really do not require the expression for computational part. What we need from this is the expression for cm. So if you look at here your cmxt is given by this. Now I can say that small cm plus 1 is given by what? Small cm plus 1 is the coefficient of minus lambda to power m plus 1 divided by factorial m. So this is the coefficient of minus lambda to power m plus 1 divided by factorial m plus 1 in, so this is coefficient. So coefficient of this in d lambda, and my claim is that this is nothing but your cmx x d of x, right. So for that it is quite obvious. So cmxt you already know, so you simply write it cmxx. So here t is given by x here, and then if you write it here, this is nothing but your cm plus 1. So I am just writing it here. So this is what, this I can write it here. I can say that one this is a m1 integral is given by this, and we have m plus 1 integral. So m plus 1 integral, and this is what, k of xx. So x x1 to xm here, and x x1 to xm here. We already have dx1 to dxm, and there is one more, that is d of x. Now what we can do here, we simply replace this x as m plus 1. So here if you change the dummy variable x by xm plus 1, then I can write this as dxm plus 1, and this is xm plus 1 and m, and you can shift this first column to last column, and this minus 1 to power m plus 1 will come out, and you can say that this is nothing but your Cm plus 1. Okay, so you can say that, okay, so here you can say that this is nothing but the expression Cm plus 1. So this we require. So we can say that what we have obtained here with this small calculation, you can say that that expression for dxt lambda and d lambda, and we can say that you can obtain C naught xt as k of xt, and that capital Cm xt satisfy this recurrence relation given as Cm xt is equal to small cm kxt minus m kxs Cm minus 1 st ds, and you can also prove that small cm can be written as integral a to b Cm minus 1 xs d of s, as we have pointed out. Now we want to summarize before using this result to find out your solution y of x. Let us summarize the discussion which we have discussed in the following theorem, which is known as Fredholm first theorem, which says that this Fredholm equation yx equal to f of x plus lambda a to b kxt yt dt, where the function f of x and this kernel kxt are integrable, then this has a unique solution y of x equal to f of x plus lambda gamma xt lambda ft dt, and where this gamma xt lambda is denoted as resolvent kernel, and it is given as a ratio of to entire function dxt lambda and d lambda, and here we have assumed that d of lambda is non-zero. So it means that we are assuming that the constant lambda is such that d lambda is non-zero, is a meromorphic function of the complex variable lambda here. It means that this gamma xt lambda is a analytic function, and it may have only singularity where this d lambda is equal to 0, and this singularity is nothing but pole kind of singularity. Okay, and here we have just seen that dxt lambda is given as k of xt, where k of xt is nothing but C naught xt, right, and you can verify that your Cm xt can be given by this m-fold integral, which is given as m-fold integral k x. So first, if you look at the first variable is x and t, rest is same as your d lambda, right. So here it is k x t here x1 to xm, x1 to xm, dx1 to dxm. So integral m-fold integral is okay. So only difference between the small cm xt and capital Cm small cm and capital Cm xt is that in capital Cm xt this is one additional column is corresponding to x and t, right, and here we don't have that. So small cm and capital Cm xt is defined as this, and dxt lambda is given by this, and small d lambda is given by this, where this symbol kxt, this symbol is denoted by this determinant, and we call this as Fredholm determinant, and this equation number 36 is known as Fredholm, this d lambda is known as Fredholm first series, and this is known as Fredholm second series. So it means that once we are able to find out this d lambda and dxt lambda, your solution can be given by this. So in next class, in next lecture, we try to find out say solution of this, and if you look at here, we have assumed that d lambda is non-zero, so we say that the homogeneous Fredholm equation will have only solution which is a trivial solution. So in next lecture, we try to find the example where we can apply our theory, and also we try to prove the uniqueness part. So in next lecture, we try to apply our theory to find out the solution, and solution which is a unique solution. So we will discuss in next lecture. Thank you very much for listening us. Thank you.